Okay, so let's talk about iterating the Pieri rules. So we've said what the Pieri rules are. Now we're going to do the following. So let me say iteration of Pieri rules. Okay, we'll see in a minute what this means. Okay, so let me start with a lemma. This is actually a corollary of the two Pieri rules. It says that the complete symmetric function hk is actually nothing but the sure function corresponding to a special partition. Okay, this is the partition sk. Okay, so all this is x, and I'm going to assume I fix some number of variables. Okay, x is just x1, x2, xn. Now, so when I say x, it's just the tuple for some n. Okay, and here this is true for all k. This lemma is going to be true for all k. Similarly, ek of x, the elementary symmetric function, is the sure function corresponding to the partition of all ones. Okay, 1, 1, 1, 1, 1 k times k ones. Okay, now why is this true? Why is this a corollary of the Pieri rules? So let's recall. So this is actually a direct corollary of the Pieri rules. So let's recall what the Pieri rule said. It said if you wanted to multiply a sure function s lambda with hk, then it told you what the answer looks like. So sum of sure functions. Let me just use the shorthand over all mu's containing lambda such that mu minus lambda is a horizontal strip. Okay, so this is a horizontal strip with k boxes. Okay, so we know what that means. You have to attach k extra boxes to the diagram of lambda such that all k of those boxes lie within the horizontal shadow of lambda. Okay, now this is the product. Now what I'm going to do here is just put lambda to be the empty partition. Okay, so let's just take lambda to be the empty partition. So this is actually a partition of the number 0. This means there are just no parts. Okay, so this is, you think of this as a partition of 0. Okay, now what does this imply? Let's just see what is the sure function corresponding to the empty partition. By definition, you're supposed to do the following, right? It's a lambda plus delta. So when you say it's the empty partition, what do you do? So recall whenever you have some n variables fixed, and if your partition has fewer than n parts, what you're supposed to do is to pad it with zeros, attach zeros at the end. So when we have n variables in the picture here and lambda is just empty, there are no non-zero parts, what you're supposed to do is to think of lambda as the n tuple, where I just pad as many zeros. So I think of it as this n tuple comprising zeros, right? So now when we look at the definition, it's a lambda plus delta of x divided by a delta of x, where delta is just the tuple n minus 1, n minus 2, 1, 0. And now observe that since lambda is all zeros, lambda plus delta is the same as delta. So this is actually the same as a delta of x. Okay, and so the answer is of course a 1. Okay, so the sure function corresponding to the empty partition is just the polynomial 1. Okay, good. So now we go back and substitute it into the Pieri rule. What does the Pieri rule say? You have to, when you multiply 1 by hk, it gives you this particular right hand side. Okay, but now let's just see what that means. In this case, it'll become something very trivial. So what's the horizontal shadow of the empty partition? So recall, what's the empty partition? So in general, if I have a partition, so if this were my partition, then what is its shadow? We are supposed to trace out its boundary, right? So this, if you wish, is the boundary, and then the horizontal segment. So you just look at which are the bits which share a side with one of the horizontal segments. So you get that as your shadow. Now if your partition is empty, then what are you looking at? Well, the boundary is just, these two bounding lines, that's all. Right? It's just the empty partition. So now what is the horizontal shadow? Well, it's just the part which shares a side with one of the horizontal segments. So it's just the first row itself. Okay. So essentially I have to attach k boxes to the empty partition such that all k boxes lie within this horizontal shadow, which means they lie all in the first row. There's only one way of doing it, which is I attach all the k boxes just like this in the first row. Okay, so this is just the partition with the single part k, and that's exactly what the right hand side is. So if you take the case when lambda is the empty partition, then the right hand side becomes a single term, which is just the Schur function corresponding to the row, the partition row. Okay, I mean by the row I mean all k boxes lie in a single row. Okay, that's the proof of the first statement. And the proof of the second statement, again I'm going to leave that as an exercise, that comes from the second Pieri rule, where in place of the horizontal shadow you're supposed to take the vertical shadow. Okay, and you can already see where that comes from. All k boxes have to be attached along the vertical side. That just means all k have to sort of go along this. Okay, so they must form a single column in that case. Okay, that's a proof of the second Pieri rule. That's a proof of the second statement, that the ek is just nothing but the Schur function corresponding to the partition 1, 1, 1, 1, 1, whose diagram is a single column. Okay, good. So we are done with that. Where does the iteration bit come from? So now let me talk about how I can iterate the Pieri rule. So recall that when we define the complete symmetric function. So let me start with a partition lambda, at lambda b, lambda 1, lambda 2, lambda l. Let's say they're all at least 1. Right? So here's a partition. And now when I talk about the complete symmetric function h lambda, so again let me just suppress the variables. This is the product h lambda 1, h lambda 2, h lambda l. Okay, now since I have a product, what I do is I just keep applying my Pieri rule again and again. Okay, so what does that mean? If I look at h lambda 1, that I have just said is the same as the Schur function corresponding to lambda 1. Now let's look at what happens if you multiply this by h lambda 2. You will just get the Schur function corresponding to h lambda 1 multiplied by the complete symmetric function h lambda 2. Now doing this, so let me just index this by the corresponding shape. That's sort of more suggestive in some ways. This is the Schur function corresponding to lambda 1 boxes arranged in a single row. When I multiply that with h lambda 2, well, I sort of know what I'm supposed to get. I'm supposed to look at S mu, where mu ranges over all partitions of a certain kind, right? Mu contains lambda, and mu minus lambda is a horizontal strip. It's supposed to be a horizontal strip of with lambda 2 boxes of size lambda 2. Right? Now, what does that imply? It means that the mu's that I will get in the second step, I will typically get many of them, okay, but they are all obtained in a certain fashion. Okay, what fashion? I write out these lambda 1 boxes. So that's the starting point. To this diagram, I attach lambda 2 boxes. Okay, how am I allowed to attach it? Such that it forms a horizontal strip, which means, so if you recall what that means, I can attach some number of boxes here, okay, and I can attach some boxes here. So I attach some, say, p boxes in the first row and lambda 2 minus p boxes in the second row. So let's just call that number p, and the leftover boxes lambda 2 minus p I attach in the second row. Okay, and now this is for all possible p's, right? There are many S mu's that I'm going to get on the right hand side. Okay, now I keep going. So that's where the iteration happens. So now I look at, okay, h lambda 1, h lambda 2. To that I multiply another complete symmetric polynomial. What will that be? Well, firstly, I already had some mu's which I got in the second step, right? These are all mu's such that mu minus lambda. So this is what mu minus the part lambda 1 is a horizontal strip of size lambda 2. So that was everything that I got in the first step. To each of them, I need to multiply in h lambda 3. Okay, now what does that mean? That will become now a double summation, right? So it's already a sum over mu, and for each mu, this is going to become a sum over partitions nu, which contain mu, and for which nu minus mu is a horizontal strip. So this guy has to be a horizontal strip of size lambda 3. Okay, now of s nus and so on. So now what is this process? So I won't describe all of it. Now you can already see what is going on at each step. So there is a certain successive attachment of boxes. So we keep getting sure functions at each step. The way it works is, at the very first step there is a single row lambda 1. In step 2 you have to attach lambda 2 more boxes, some of which goes here, some of which goes here. Okay, in step 3 let me use a different color. I have to attach lambda 3 boxes total. Okay, and those boxes, well, some of them can go here, some of them can go here, because that's the mu's that I got in the preceding step, and then some of them can go here. So if you sort of look at what the horizontal shadow of this part mu means, so let's try to highlight the mu that we got in the previous step. So this was the boundary, the outline of the mu. To that I have to attach lambda 3 more boxes, right? So that's the attachment that I've just performed. So this is some extra boxes here, lambda 3 of them. Okay, and so on. So now let's do lambda 4. Let's see, white. So I attach a total of lambda 4 additional boxes. They can go like this, and so on. Okay, so this is the successive attachment of boxes. So let's just write out how many of each kind. So the number of white boxes, there should be lambda 4 white boxes. Okay, how many green boxes did we attach? Sorry, it's a different color. Okay, green boxes were lambda 3 in number. Okay, the red boxes were lambda 2 in number, and of course the yellow is the original, the starting point more or less, which had lambda 1 boxes, and so on. So you can see that this process continues. At every step you attach lambda I boxes, all of which lie within the shadow, the horizontal shadow of the shape that has been formed until the previous step. Okay, and observe there are many ways of doing this. The number of, even attaching red boxes, there are lots of ways. It depends on how many you choose to attach in the first row and how many in the second. The green boxes, how many you want to put in first row, second row, third row, and so on. Okay, that condition about horizontal strip has to be satisfied. Okay, good. So now this is the basic idea. Okay, so this is the iteration. And when you iterate all the way to the end, h lambda 1, lambda 2, lambda 3, all the way to lambda L, the final answer is just going to be a sum of sure functions. Okay, but what sure functions are you going to get at the end? Well, they are going to be exactly the sure functions indexed by all possible final shapes that can be obtained by this process of successive attachment of boxes. Okay, so this is successive attachment of horizontal strips. That's what it means. Okay, so let's just say that verbally. So if I take so h lambda 1, h lambda 2, h lambda L is the following. It's a sum of sure functions s, let's give it a name, s gamma, okay, let's call it s gamma L, we just call it gamma itself. Now what is gamma? maybe I'll call it gamma L, the shape I get at the Lth step. Okay, so what are gamma L? I mean, where does this sum range over? It ranges over all possible gamma L's, the final shapes. But what are gamma L's? How are they obtained? Well, gamma L is the last shape that you get when you form any such tower of shapes. Okay, so the sum really, think of it as follows: the sum is really over towers, or so let's say it's a sum over towers of the following kind, towers of shapes. First is the empty shape, followed by some shape gamma 1, followed by another shape gamma 2. So these are the shapes that I get, and gamma L is the very last member of this tower. Okay, the summation here is actually running over all possible towers of shapes, and the Schur function is indexed by the very last element. Okay, it's indexed by the final shape of the tower. But then what are the towers? The towers are formed according to the following rule, such that if you take any ith step, you look at gamma I plus 1 minus gamma I. Okay, how do you get gamma I plus 1 from gamma I? So I should say this is a horizontal strip of size lambda I. Okay, so this is for, so this last guy I call gamma 0, the first guy I call gamma 0. Okay, so this is for I equals, let's see if this is correct, gamma I by I minus 1. Gamma I by gamma I minus 1. This is a horizontal strip of size lambda I for all I ranging from 1 to L. Okay, so what have I done? Essentially, I am saying the same thing that I have said earlier, which is that you form a tower of shapes. Okay, the very first step is the empty shape. To that you attach lambda 1 boxes. Okay, now from that to that you attach the next guy. So what's the tower in this case? The tower is just going to be, the first step of the tower is lambda 1. The second shape in the tower is the thing formed by lambda 1 and the red boxes. Third shape in the tower is everything plus the green boxes. The fourth shape is everything and the white boxes, and so on. Okay, so it's a successive, it's a nested sequence of shapes such that the differences at every step form a horizontal strip, okay, with exactly lambda I boxes. So that's exactly what the iteration is telling us. Okay, very good. So that is the definition. I mean, that's what the Pieri rule gives us, and we will rephrase this as follows. So let's write it as therefore H lambda. I'm going to summarize. H lambda is therefore the sum of, so let me call it as mu here. It's a sum over all, well, over all mu's, okay, of a certain number. Okay, so this number here is what's called k mu lambda. Okay, where what is this number k mu lambda? K mu lambda by definition is the following. It is the number of towers of the kind that we just talked about, empty, gamma 1, gamma 2, gamma L, such that gamma I minus 1, so this guy is gamma 0, is a horizontal strip of size lambda I. Okay, the lambda I is the ith part of this lambda here. And where does the mu come in? The mu is the end point, and gamma L is equal to mu. Okay, the number of towers going from the empty shape to the shape mu, such that at every subsequent step you are adding lambda I many boxes. So that number, the number of such towers, is what's called, it's given the number, it's given the notation k mu lambda. Okay, and this is called the Kostka number. Okay, so the Kostka number measures the number of such towers, if you will. Okay, good. Now it turns out that this can, one way of thinking about it is in terms of these towers, but there is another way of thinking about it, which is sometimes nicer, and that's really the following. So let's look at this picture again that we drew earlier of the tower of shapes, and let's do the following. So we will take this first shape that we got, okay, that was the yellow, and we'll do the following. We will just, so there are some boxes, of course, we will fill all those boxes with the number 1. Okay, so the number 1 just tells us that was the very first shape in the tower. Okay, and then we move on to the next one. So we have the red boxes next, the ones that were attached to the tower in the next step, and we'll look at all the boxes there and number them with the number 2. Okay, now the green boxes get the number 3. It's the number 3 here, 3 here. So now the last, well, in this case I've only drawn it until this point, so the white boxes get the number 4. Okay, now we look at this final the final object that we get. It's now, it's the shape with some boxes numbered 1, 2, 3, 4, so that it tells us, from this we can read off the tower, right? So we sort of know which boxes were attached in the first step, which boxes were attached next, and so on. Now the fact that at every step what you are attaching is a horizontal strip, okay, means the following. If you sort of think about what a horizontal strip really is, so let's see if I have a color here. Let me use, okay, let me just use blue here. So what does it mean to say that I've attached a horizontal strip at every step? So just look at the 2's that we attached. The 3 of them were there and the 4 of them are there. Okay, so what it means is that no 2 of them is in the same column. Okay, so the boxes, the ones attached in the second step, no 2 of those boxes can be one below the other. Okay, they can't be in the same column. Same thing with the 3's, right? So next step, it's again a horizontal strip. The 3's span many rows, but they are never one above the other. Okay, so they cannot be in the same column, and so on. Okay, that's really what a horizontal strip means. Okay, if you go back and look at the definition, the horizontal shadow just means it should share a vertical edge with the boundary of the preceding shape. Okay, so what that means is that along the rows, what I'm doing, since I'm only adding boxes at every subsequent step, so the numbers along the row will keep weakly increasing, which reflects the fact that they were added at subsequent stages, and the numbers along the columns have to be strictly increasing. Okay, why is that? Because I cannot get a 2 and a 2 one below the other. That's never going to be possible. So two numbers in a column can't be equal to each other. That's what horizontal strip means. Okay, and again I'm attaching boxes at later and later stages, so the numbers are definitely weakly increasing, but because it's a horizontal strip, it's also that I cannot have 2 2's occurring in the same column or 2 3's and so on. Okay, so this discussion says the following, that this number, the number of towers, is actually the same as the following. This is equivalently the number of fillings. Okay, fillings by numbers, fillings of, and what is the final shape that I have? So recall at the very end, the final outline is the shape mu that I am interested in. So I have to take the shape mu and I fill the boxes of that shape with some numbers 1, 2, 3 and so on. Okay, number of fillings of the shape mu with numbers 1, 2, 3 till L. Okay, so if you observe, what's the very last one? H lambda 1, lambda 2, lambda L. That L is going to be the very last guy I'm going to fill. Okay, number of fillings with the numbers 1 to L such that the following conditions hold. The rows, after you filled it, the row numbers, the numbers along the rows are weakly increasing and the numbers along the columns are strictly increasing. Okay, and further, the filling that I make has the following property. There are lambda 1 1s, lambda 2 2s and so on in the filling. Right, that's what it means to say I attach lambda 1 boxes in the first step, lambda 2 boxes in the second step, etc. Okay, so this is the final outcome, that this Kostka number. So this is the Kostka number k mu lambda. It says you take the shape, outer shape mu, fill it with lambda 1 1s, lambda 2 2s, lambda 3 3s in a very special way, such that the numbers on the rows are weakly increasing, the numbers down the columns are strictly increasing. Okay. So now any such filling which satisfies these conditions is called a semi-standard tableau. Okay, and that's the title. So here's the definition. A semi-standard tableau of shape mu and type lambda, okay, is a filling which satisfies these conditions. It's a filling of the shape mu, okay, of the shape mu with lambda i's, okay, satisfying those two properties. Entries are weakly increasing along rows to strictly increasing along columns. Okay, so what this means is that what we have just shown is that k mu lambda, this Kostka number, therefore, is, what is this? This is the cardinality of the set. So let me call this semi-standard Young tableau of shape mu and type lambda. Okay, and as you sort of saw when we defined the semi-standard Young tableau, it's just another way of thinking about these towers of shapes which are successively attached following that horizontal strip rule. Okay, so that's the that's the very first Pieri rule iteration. You can of course iterate the second Pieri rule similarly, and let me just quickly state what that theorem will look like. So it will say that if lambda is a partition of D and you want to write E lambda, so lambda is lambda 1, lambda 2, lambda L, then E lambda, which is the product of E lambda 1 with E lambda 2, E lambda 3 and so on, will likewise become a sum of sure functions S mu, and now each, what are the mu's? The mu's are just going to become, how many mu's will you get? The sum again is over towers of shapes, gamma 1, gamma 2, gamma L being mu, final shape, such that gamma I minus 1 is a vertical strip, not a horizontal strip anymore. Okay, it's a vertical strip of size lambda I. Okay, by the same reasoning, that's how the second Pieri rule works. You have to keep attaching vertical strips to the preceding shape. And so you can see that this is therefore, by a similar token, what is it? At every step, initially you have lambda 1 boxes along a column. To that you have to attach lambda 2 boxes, but like this, then lambda 3 boxes like this, and so on. Okay, so the same sort of successive attachment rule works, except now it's to be done along columns rather than along rows. Okay, and of course one can just go back and redefine everything the same way. You can talk about maybe semi-standard column tableau and so on, but it's actually more convenient to define this notion of a conjugate of a partition which interchanges rows and columns. Okay, and then we can just have one notion. So let me just quickly tell you what the conjugate of a partition is. So if I have a partition lambda 1, lambda 2, lambda L, the conjugate is the partition obtained by interchanging rows and columns. Okay, so let's just do it pictorially. So this is my shape with, say, lambda 1 boxes, lambda 2 boxes, lambda 3 boxes. Let's do it by example really. So this is now 1, 2, 3, 4, 5. So lambda is 5, 3, 2. Right? That's the partition. Then the conjugate is the following. You just sort of interchange the rows and the columns. So you think of it as 3, 3, 2, 1, 1. So I just draw the first row of the conjugate is just the first column of lambda. So 3, 3, 2, 1, 1. Okay. So this is called lambda prime of the conjugate of lambda. It's just 3, 3. Okay. So interchange rows and columns. That's what conjugate means. Okay, good. So now having defined this, now it's easy to see what the second Pieri rule on iteration gives us. It says that so the theorem that I talked about earlier can be rephrased as follows. If you want to write, so let lambda be a partition of D. If you want to expand E lambda as a linear combination of sure functions, then this number here that you're going to get the coefficient, sum over mu. What is this number? Well, as we just saw, it's you take, you keep attaching successive boxes in this way till the final shape becomes the shape of mu. Okay, so this final shape is mu, but since I want to somehow say what it means to, I want to express my coefficient in terms of semi-standard tableau, what I'm going to do is just look at, the conjugate of this shape. Okay, so in order to say, my final shape is still mu, but I have to fill the fillings that I'm going to talk about are the following. So what's this is my question. So the fillings are, they weakly increase along the rows and strictly increase along the columns. Okay. Sorry, that's the usual semi-standard tableau. So now it's the other way around. They weakly increase along the columns and strictly increase along the rows. Okay. So in order to make this into a usual semi-standard tableau, what I'll do is I'll conjugate this filling also. So I'll think of it as, okay, I'll put all the first column into the first row. Then these additional boxes that were attached, I'll think of them as being attached along the rows and so on. Okay, now when I do this, what am I getting? This is my original shape mu, and this is the conjugated shape mu prime, and mu prime is now being filled with lambda 1 1s, lambda 2 2s, and so on. So observe, I am still filling it with lambda I i's. Okay, so this semi-standard tableau now that I am talking about here, what is this number? It is the number of semi-standard tableau whose final shape is mu prime and whose type is lambda. Okay, so I've just rephrased this. I've just conjugated my shape so that I don't have to invent a new notion of semi-standard column tableau. Okay, so that's the final answer here. E lambda is summation k mu prime lambda s mu, where k mu prime lambda still means the same thing. Semi-standard tableau in the usual sense, with final shape mu prime and whose content or type is lambda. Okay, so finally let's just do one example to see how this whole iteration business works out. Let's just do it in one single case of age. So if mu is 3 2, okay, so let me just try and expand that age out in full. So here's what I want to do. I want to take the partition 2 2 1 and try to write the corresponding complete symmetric polynomial in terms of the sure polynomials, right, by iterating Pieri's rule. So what's what am I supposed to do? When I first do h2 remember is just s2. Now when I multiply this by h1, so Pieri's rule tells me I first take this, to which I attach a single box either here or attach it here. Okay, so sorry, h2 1 1, sorry. So 2 1 1 is h2 h1 h1, so I have to attach a single box there or there, and so maybe we should also put numbers. These were the two boxes attached in the first step. This is the box attached in the second step, right? And then okay, I mean, that's not okay. Let me not confuse you with putting numbers there. So all I mean is, the shapes that I get after two steps, I can think of it as having been obtained like this. Okay, and now I need to attach one more box, right? So that's my third step when I do h2 h1 h1. So that is like, okay, where all can I attach that additional box? I can either attach it there, or I can attach it downstairs. Similarly here, I can attach it in three different places. So it's 1 1 2 3, or 1 1 2 3. Okay, so these are all the final answers that I get. These are all the different tableaux. Okay, and observe that this particular shape, so there are two of them of this shape. Okay, so if you're going to write the final answer in terms of sure functions, here's what it looks like. h2 h1 h1 is the sure function corresponding to, so let's look at this guy. This is the shape 1 2 3 4 boxes, right? So this is just the sure function corresponding to 4 boxes, plus the second guy, this is 3 boxes and 1 box. This guy is also 3 boxes and 1 box. So this is the partition 3 1, but there are 2 such terms which contribute to it. Okay, so it's 2 times that. Now this is the partition 2 2, and the last one is the partition 2 1 1. Okay, so I get S 2 1 1. So that's the final one. Okay, that's done.